Hello, my name is Romain, and I'm here to present our work Dextrems in collaboration with Shan-Yuan Teng, Pengyu Li, Yujie Tao, and my advisor Pedro Lopez at the University of Chicago. Let me first show you a short clip of Dextrems in action. On the right side, we have a person with hearing impairment, spelling out "What's your major?" in American Sign Language. The person on the left does not understand sign language and uses their smartphone to translate the question, then type in their response. Dextrems interprets the message and starts spelling out the letters by actuating the user's finger. We can see here a letter H being spelled out, then C, and finally I. Traditionally, the way to actuate the hand is through an exoskeleton. In order to produce force feedback, exoskeletons need enough force to push back against the fingers, meaning their actuators tend to be big and heavy. Dextrems, on the other hand, uses a lightweight exoskeleton that not only locks the finger joints on demand, but utilizes muscles as the main method of locomotion, using electrical muscle stimulation. Now let's break down on how Dextrems is actuating the fingers to render the letter I. First, the exoskeleton locks the pinky finger with the mechanical brakes. If we zoom in closer, we can notice a ratchet mechanism being engaged. This will lock the finger in place. Then Dextrems move the other fingers through EMS, with electrodes attached to the forearm. Notice that the index, middle, and ring fingers contracted, but not the pinky. This is because the pinky was locked by the mechanical brakes. Finally, to achieve a stable pose, the remaining fingers are also locked. But wait, let's rewind for a second. You're probably thinking, why can't we just do this with EMS alone? Let's try to find out. We're going to spell the letter K in sign language by using only EMS. The letter K can be spelled by flexing the ring and the pinky fingers, like such, and keeping the index straight and the middle finger around at 45 degrees. Now, fully flexing the ring and pinky fingers is easy with EMS. However, posing the middle finger at 45 degrees is very challenging. To achieve such precise actuation, researchers move the muscles on both directions, the pushing side and the pulling side, trying to balance out the forces to stop the fingers at a precise location. Electrodes are placed both on the explexor and the extensor. Fingers are actuated until they reach their target position. Notice here that the index moved from its initial position even though we did not actuate it. This unwanted movement is caused by EMS running through adjacent muscles due to the way they are layered and bundled around the forearm. When the ring and pinky fingers are fully flexed, we just stop EMS. As for the middle finger, it is actuated until it reaches its target angle. If the finger overshoots, the opposing muscle, the extensor, is actuated to compensate for the errors. The same applies when the finger undershoots with the flexor. However, here, as seen in the video, keeping the finger at the correct angle is very hard and causes unwanted oscillations. This is because finger muscles are very sensitive to electrical stimulation. Now let's look at how Dextrems achieve such pose. First, the exoskeleton locks the index to prevent it from moving. Then we apply EMS on all four fingers. Because the index is already locked into place, the remaining fingers are able to move with EMS actuation. This solves the first issue we had with EMS only, where applying EMS on one finger can affect others. Once the finger reaches a target angle, the exoskeleton locks them into place to retain a stable pose. Unlike the previous implementation, we don't need to balance the forces since we're using mechanical locks and we can simply just turn off EMS. This means there's no oscillations and therefore solves our second problem with EMS only, where we saw oscillations. Now let's see both implementations side by side one more time. We implemented Dextrems as a wearable device combining EMS with a brake exoskeleton. We want to utilize the precision of an exoskeleton and add EMS, a low-profile lightweight actuator. The whole exoskeleton weighs in at 68 grams, including the battery, which is significantly lighter than traditional exoskeleton, such as this one, weighing close to 1 kilo, and that excludes the battery. Our design includes 3D printed linkages, a custom PCB, a LiPo battery, Bluetooth, and 8 mechanical brakes. 4 at the PIP joints, and 4 at the MCP joints. As usual, electrodes are placed on the forearms and connected to a muscle stimulator. Now let's take a closer look at this joint to understand how the mechanical brakes work. It is based on a simple one-direction ratchet system where we have a ratchet connected at one end of the finger, a pawl at the other end, and a small DC motor in charge of jamming the pawl into the ratchet. When the pawl is disengaged, the joint can just move freely. But when the pawl is engaged into the ratchet, the joint is locked into place and cannot flex any farther. The dextrams can also lock in the opposite direction. To do so, the device engages the brake at the joint. When it moves in the opposite direction, the brake mechanism will not lock, but rather slip on the ratchet. Then EMS is applied to the extensor. When the position is reached, we just turn off the EMS. The hand will naturally want to recoil back into its resting position, but since the lock's already engaged, the joint will just be held in place. To better understand dextrams, we conducted 2 technical evaluations. In our first one, we evaluated how each joints are independent to each other and compared it to traditional EMS only. We found out that dextrams doubles the independence of EMS, in average. In our second evaluation, we measured and compared the amount of oscillation and precision, and found out that dextrams has similar precision to EMS, but significantly improved the unwanted oscillations. However, some oscillations still remain due to the mechanical slack of the exoskeleton. All that is great, but what can we actually do with dextrams? As we already saw with the finger spelling, this unprecedented precision enables application previously not possible with the EMS alone. For instance, dextram is great for VR applications that require force feedback on individual fingers. In this whack-a-mole game, our device can render the mole shape, just like a traditional exoskeleton would, by locking the joints when a collision is detected. But when the mole fights back by raising its right hand, the user's index gets pushed upwards by our device. Dextram is also very useful to teach skill movements, for instance learning how to play the piano with individual fingers movements, or even learning how to play the guitar. Dextrams can shape the hand into the position of a chord. Then EMS is applied to push the finger onto the fretboard. And from there, the brakes are engaged to prevent the fingers from moving. Finally, the user can strum the strings with the right hand and play an E minor chord for the first time. Dextrams follow a long line of research in our lab. We're trying to integrate devices with our body and not rely on heavy external exoskeletons. Instead of adding more electronics that externally induce sensations, we only add the minimum components to trick the user's biology into internally inducing the sensation. As you can see, here we're not the only one thinking about EMS as a promising alternative to mechanical force feedback. Unfortunately, all these systems offer very coarse actuation, typically just coarsely actuating large muscle groups like legs, arms, or wrists, nothing with the precision needed for high-skill finger manipulations. My colleague Akifumi Takahashi recently tackled the same challenges of EMS at Kite 21. By placing the electrodes at the back of the hand, he actuated the fingers independently. However, the fingers could only move in the extension direction and only at the MCP. It also does not solve the oscillation problem. The dextram, on the other hand, takes this a step further by actuating fingers in both flexion and extension, and also at the MCP joint and PIP joint. To conclude, we increase the dexterity of traditional electrical muscle stimulation by proposing and engineering dextrams, an EMS-based haptic device combined with lightweight mechanical brakes attached on each finger joint. While we have shown dextrams on the hands, which is considered as one of the hardest limbs to move around with EMS, we can also expand the system onto larger body parts such as arms or legs, allowing us to eliminate the need for large and heavy actuators. We made dextrams open source, which can be found at the link shown on the screen. We hope that our device inspires many, and we're excited to see what comes next. Thank you for listening to our talk. Please stop by our demo session and check out our paper for more details.